time we were on this slide, and basically we talked about how the security policy database and security association databases are used. So security association is a connection actually over IP between the two end systems. It's a one-way connection, and each association is specified, given a number which is called as SAI, and Security Association ID, and so that database is kept, right? So now we are going to talk about tunnel. Now the term tunnel, actually you probably already all know, the tunnel is another name for encapsulation. So the tunnels are used in IP whenever you have to pass through a region or through a subnetwork or through not subnetwork, through a network where some feature of the IP is not used. For example, if you are going on IPv6 and you have to pass through a network IPv4 network, then you will do a tunnel, and the vice versa. If you are going over IPv4 and you have to pass through IPv6 area, you use a tunnel. And so the tunnel, the way it works is that you take the original packet, original header, and you put it into a new packet with a new header, and that new header is spoken in that area where you're passing through, and when you pass that area completely, at the exit you decapsulate the packet. One way to understand this is, let's say you have a packet written with English address which is going through Japan, and in Japan just assume that they don't understand English for a minute. And so what we will do is, as soon as the packet enters Japan, we will put the packet inside another envelope and put an address, exit address in Japanese. So the packet will be forwarded all the way through Japan to the exit port, where they will take out the packet or outer envelope, and now the packet can go forward in English. Okay, same way, any little feature which makes it difficult for the packet to go through any area, we use tunneling, and another name for tunneling is encapsulation. So one way or the other, basically when we say we are going to tunnel, which means that we are going to put the packet inside another packet. So IPsec basically uses tunneling, as we will see in a minute, and so it's a series of proposals from IETF, and it separates the authentication and privacy. So authentication simply means that guaranteeing that the packet has not changed, and privacy means encryption. So you can do either one or both, and so there are two different alternatives. One is called authentication header, which ensures that the data integrity and data origin authentication. So basically it ensures that you can be sure that nobody has changed the packet and that the packet came from the source that it says it came from. The second is ESP, encapsulating security protocol. The name doesn't really tell what we are talking about, but basically this is encryption. So it ensures confidentiality, data origin authentication, connectionless integrity, and anti-replay service. So this is basically offers everything that AH does and more. So it includes, ESP includes data origin authentication, it includes integrity, and it also includes confidentiality, which means encryption, and then it has anti-replay and other things. So depending upon how much security you want, you select one or the other. Generally, in fact, you could do both, as we'll see later on. And so the packet looks like as shown in the bottom. There is the original data. There is the original header and it says star optional. So we will see in some cases we can remove the original header. And then we have ESP header, and then we have AH header, and then we have the IP header. So basically in the front of the packet we have IP header, inside that you have AH, inside that you have ESP, inside that you have the original header if included, and you have the data. Now you don't have to have both AH and ESP. As I said, that you might just have AH, or you might just have ESP, or you might have both. So the question is why we want to remove the headers, original header in some cases. And before I get to the next slide, just notice that this part is encrypted and it is shown in a hashed area, right? And whatever is shown in clear is in clear. So this is encrypted and this goes in clear. So there are two ways you can use IPsec. One is that each user has IPsec end-to-end, and they set up a connection, a secure connection end-to-end. Another one is that users really don't know anything about IPsec and they don't care, but the company does, and the company has the routers which do the encryption. So before the packet goes out in the outer world, the packet is encrypted or AH, whatever, and then at this end it is de-encapsulated, right? So this is called gateway to gateway, and this is called end to end. Gateway to gateway is called tunnel mode, and the end to end is called transport mode. Again, the name really is not very indicative. So suppose somebody told you that we are going to using transport mode, then it is difficult to say, well, that means end to end. But the reason you can associate it that way is that the transport is TCP or UDP or whatever, but they are generally end to end. And so if you want to remember that the transport mode means end to end, whereas the other mode, tunnel mode, means there is some area where you want to be protected, but inside the company you don't want to be protected. So you pass through using the tunnel. Now, although there is encapsulation in both cases, it's a different kind of encapsulation, as we will see this year in the year. So in the tunnel mode, we take the original header and put it inside the packet. So the rest of the packet is there, the original header is there. Then we put the IPsec header, which could be AH or ESP or both. And then we have the new IP header. Okay. Why do we need new IP header? Because this packet is not going end to end. This packet is going from this router to that router. And there might be many routers on the way. But the packet is going from this router to that router. So really the source for this packet is this router, and the destination for this packet is this router. Those are the only two which have the keys to handle this packet, that have the secrets to handle this packet. And therefore this new IP header has the source address of this router, the left router, and the destination address of the right router. And so this is why we need the new header, and we keep the original header inside so that once the packet is decapsulated, we know where to send it next, where the real destination is. Okay, so this is the tunnel mode. In the transport mode, the routers are not involved. We already have the correct source and destination in the header. So we don't need to put that inside IPsec. We can put that here, and we can have rest of the packet here and the IPsec header in the middle. Okay. And I have not shown anything encrypted here, but basically depending upon what kind of security you have requested, this part of the packet, the rest of the packet, or in this case IP header and the rest of the packet might be encrypted. Okay. Any question about this slide? So is this clear when we use tunnel mode and when we use transport mode? Tunnel mode, so for example, if you are doing VPN from home, what mode are you using? When you are doing VPN from home, you are actually using transport mode because your computer is running one end of the VPN and the other end is at whatever host you have VPN to. Whereas if you work for a company and you are sending a packet, let's say from Seattle to St. Louis, I'm taking the Boeing example. In that case, you probably are not doing any VPNing, but Boeing is doing it for you, and that would be tunnel mode. Okay. All right. So now you understand the two modes. So let's go into the authentication header. Authentication header starts with the first 8-bit field called next header. Now, I don't know if you guys have ever heard of the word next header before. Does anybody remember hearing next header in 473? Yeah. Where is it used? I can barely hear it. Is there a small microphone nearby someplace? IPv6? Okay, well that's the answer. So basically, if you remember IPv6 has many headers. IPv6 has many headers, and each header starts with the next header field. So this is basically a IPv6 style header, although it is also used in IPv4, by the way. So whether it is IPv4 or v6, AS header starts with the field called next header, and that clearly indicates what is the payload. Basically, that indicates what is inside this. Okay, basically it's stuff which I mean, it is not straight data. It could be some other header. Then there is payload length. Again, payload here means whatever is inside, and not only the data. The next 16 bits are reserved. Next 32 bits are SPI, security parameter index. So this is a number. Remember, all this goes in clear. This is not encrypted or anything. All of this goes in clear. So the security parameter index is a number which says what table entry in your SPI database you should look at. So if the number is, let's say, 2033, then you go to 2033 entry in your table and find out what the keys are. Keys, etc. are not sent here, right? So these are just the association number. Then sequence number. So each packet is numbered from 0 onwards, and so basically that is the sequence number. And then authentication data. And so the last thing is what we call integrity check value, ICV. And ICV basically is MAC, message authentication code, which if you know the key, then you can calculate it and verify it, and that verifies that the data was not changed and that the data came from the source who knows the secret. Okay, so this is straightforward. Basically, let's see. Some of the SPI values are reserved. So 1 through 255 are reserved. SPI values are 32-bit long, so they can be quite a bit big values. So the 1 to 255 are reserved, and the 0 is not used. Okay, so local use. So basically, the payload length is, now this is something that you have to remember, and this is kind of, I think it is kind of crazy, but anyway, payload length is the length of the AH payload. Length of the AH payload, actually, remember, length of the AH payload in 32-bit words. So you take whatever number of bytes there are, divided by 4, that gives you length of the AH payload in 32-bit words, minus 2. Then you subtract 2 for the IPv4. In case of IPv6, you divide it by 64 and subtract 1. Okay, and so anyway, one of the things that we generally ask in the exams is we give you the payload length and ask what is the length of the payload really in bytes. So you have to just remember this magical thing is that if it is IPv6, add 1, multiply by 8. If it is IPv4, add 2, multiply by 4. Okay, so you should be able to translate the payload length into bytes. And okay, so that's all there is. The next header is basically the protocol type. So this is the same protocol type that we use in IP and TCP and everywhere else. If in IP header, if you have the protocol type field 6, that means TCP. If you have protocol type 17, that means UDP. Protocol type 4 is IP itself, 51 is AH. So in this case, what will happen is the IP header will say protocol type field of 51, and the next header field will probably say 6, which is TCP. Is that clear as to how the protocol type field is used? Basically, protocol type is same as payload type is same as next header. So the next header tells you what is inside this packet, and which could be a TCP packet, TCP segment, you know, or it could be UDP, or it could be anything else. So every protocol has a number. Okay. So we know the next header, we know the payload length, we know how to use the SPI and so on. So integrity check value. So that's all there is. There is no encryption in this case, right? Okay. So how do you compute the integrity check value? That's a little bit tricky. And the trick is that the integrity check value covers the entire packet. It covers the payload. It covers the old IP header if it is included. So that's optional. That's why it is shown in the square bracket. And the hashing doesn't mean encryption here, but basically that is the part that is protected. I mean, that is, okay, so right now there is no encryption for a minute, okay? And then there is AH header, which we saw in the previous slide. And then there is a new IP header, or the old IP header. Anyway, so the whole thing is covered by ICV. If any bit changes in any of these fields, ICV will not match. Now the problem is that the IP headers change all the time at every hop. There is a hop count value in the IP header, which is decremented at every hop, and there are other values which change at every hop. And so how do you ensure that the IC value will come out correct at the other end? And so we divide the header fields into immutable or predictable. Okay, so the fields that are either immutable in transit, immutable means that they will not change, or that are predictable upon arrival, are things that we can say what their value will be on arrival. Then, and by arrival means arrival at the end point of the AH SA. So the SA could be router to router, or SA could be end to end. So depending upon, so at the arrival, if we can figure out what the value is and was, so those things we include in the ICV, things that we know will change anyway, and we cannot predict what their value will be on arrival. We zero them out first. So let's see, source address is an example of immutable address. So the source address of the packet when it starts at the beginning of the AH association will remain the same until the end of the AH association. And therefore, that will be included. Destination address with source routing. Now, here's the thing. If you have source routing, then the way source routing works, again, this is something in 473 they might have taught you, is that you put the whole route in the packet. and then at every hop, the next router becomes the destination. So you go from one router to the next specified router to the next specified router to the next specified router. So that way the destination address keeps changing, but you can tell that at the end what the destination address will be. So it is predictable, right? So you put that value. Now the AH header, next header, payload length, reserved SPI, sequence number, and authentication data, which is set to 0 for this computation. So what you do is the authentication data IC value itself is set to 0, and if there are any padding bytes, those are all included in addition to immutable and predictable values. And so that is what ICV covers. So the AH ICV computed over the header, the upper level protocol data, which is assumed to be immutable in transit. So everything is covered from here to here, except those values that will change and we cannot predict will be set to 0. And the ICV value here will be set to 0. And then we will compute the ICV and put it there. Okay, so is it clear that why some fields are excluded from the ICV, are zeroed out, not actually excluded, but zeroed out before ICV computation? Right? In particular, a field called hop count. Everybody knows how the hop count is used, right? Hop count will be what kind of field? Will it be included or will it be zeroed out? Can anybody answer? Nobody knows this? Wow. What is hop count used for? Okay, so let me ask this. Has anybody ever heard of the word hop count in the IP header? They have heard. So what it is used for? Why is it used? Why is it put in the first place? Yeah, but so basically the main purpose is, that's good. The main purpose though is to avoid looping. If some routers have a wrong table, they might send it backwards. And the packet will come back, and they will send it backwards, the packet will come back, they will send it backwards, the packet will come back. And so the hop count will exceed. And then the packet will be thrown away. Right? So the purpose of the hop count is to avoid looping, and it is decremented at every hop. So every router, regardless of what is in this table, decreases it. So even the router which has the wrong table will decrement it, and then the packet will eventually be dropped. So that is a field. Clearly, we don't know how many hops it would have covered, because even if even if you measure the number of hops first time for a packet, the second packet may take a different route and may have a different number of hops. So hop count cannot be predicted in advance. So that is a field which has to be zeroed. Okay, so that would be a field which would be called mutable and unpredictable. Right, changeable and unpredictable. So that's the thing, you cannot predict it. So that field has to be zeroed. And if something can be predicted, we put the last value. If something is not changing, we could, of course, leave it alone. So that is how we calculate the ICV. All right, any question about this? Yeah, go ahead. Is somebody raising hand? I thought somebody was raising hand. All right, if nobody has a question, then we move on to AH version 3. which is the latest version, and it came in 2005. Basically what it does is it has a specified algorithm as to how do you compute SPI, how do you set the SPI for unicast and multicast. For unicast, obviously you just use SPI alone or SPI plus protocol type to select the SA. So you might have an agreement with the destination that we have one security association. However, we are going to have many different protocol type. I might send you TCP packets, I might send you UDP packets, and I might send you some other packets. So the protocol type field plus this number will give you the what association I'm talking about. So you don't have to have many SAs. On one SA, you will have different SPIs. Okay, so this is like aggregating all the SAs, multiple SAs into one. So you can either use the SPI alone or SPI plus protocol type to select the SA from your table. In the case of multicast, you use the destination address. Now, destination address in this case is a multicast address. Remember, destination address is a multicast address. So you might just use the SPI which is specified plus the destination address, which could be, you might have many different multicasts. So that would distinguish them. Or you could have destination address and source address. Why that? Because there are multiple sources as well, quite possible in this multicast discussion that we are having, or communication that we are having, there may be many sources are talking. And so each source will have a different secret and could have a different something. So basically SPI plus DA plus SA. So one of those possibilities can be used. Third thing that was done in AH version 3 is that the speeds are becoming too fast for the network, and the 32-bit sequence numbers can cycle too fast. So they started using 64-bit sequence numbers. Now if you remember here in the old one here, the sequence number is 32-bit long, 0 to 31, 32-bit long. And so in AH version 3, they have 64-bit sequence numbers. And then there are some algorithms which are mandatory. So basically, this is the same issue. Whenever you select any security thing, you have to decide, you have to tell what algorithms can you implement or understand, which encryption, which hashing, so on and so forth. So there are some algorithms which are mandatory. Everybody has to implement those. And so there is a separate RFC which specifies what those algorithms are. Okay, so AH version 3 basically has a uniform algorithm for SPI, and then it has 64-bit sequence numbers, and then it has mandatory algorithms which everybody has to implement. That finishes AH. Any question about authentication header? If not, we move on to ESP. ESP provides a lot of stuff. As you can see, 7 different services here. It provides confidentiality, which means encryption. It provides data origin authentication, so you can authenticate who knows the secret. Connectionless integrity, and basically you can have the MAC or the message authentication. Anti-replay service. So nobody can replay the same packet, which is basically there before as well. Limited traffic flow confidentiality. So we had talked about traffic flow confidentiality, I think last time, when you didn't want people to know how many packets have been sent, or what size packets have been sent. So the people looking at the traffic, even though they can't read the packets, they can figure out that something is going on. With this, there are things that you can do to avoid, to confuse, basically, not really avoid in some sense, but to confuse. And then service depends upon the option selected when establishing the security association. So basically, when you set up the security, then you decide which of these services you want, right? And can use a variety of encryption and authentication algorithms. So that is common among all these things anyway. So those are the different things ESP can do. ESP packet again has something like, same thing like we saw before, which is next header. However, the next header is not at the beginning, and I don't know why they just put it at the end. So it starts with SPI, then goes the sequence number, then they have IV, the initialization value, then they have the whole packet, and there is a trailer. The trailer consists of the padding and TFC padding, which we will explain in a minute, but basically then there is a padding, pad length, and then there is a next header, and then there is ICV. Okay, so this is TFC stands for Traffic Flow Confidentiality. So traffic flow confidentiality padding, as the name indicates, is basically to change the size of the packet. So you might be sending a small packet which can tell somebody that this is either a request or this is an acknowledgement. If it is a large packet, it could be a response. And so what you do is you can make all packets large, and nobody can distinguish a request from a response or an acknowledgement from a packet. So TFC padding is used for that purpose, for the traffic flow confidentiality. This is the feature for traffic flow confidentiality. The regular padding is simply to make everything multiple of 64 bit. And then the ICV is already there. Next header we already know. So I think we know all of the fields in this header. Let's just go one more time. We know what is SPI. It helps us figure out which entry in the table to look at. Sequence number, what is the packet number here? Initialization value IV is used in many of these encryption algorithms. And then